Have you ever been to a demolition derby? Basically, bunch of people driving cars around a field doing their best to ram into each other while protecting themselves as much as possible. The goal, of course, is to damage the other car so badly that they can't be driven anymore. The driver of the last operational car wins. Chemical reactions basically work just like this. Atoms and molecules move around their environment, occasionally ramming into each other. If they do it just right, a reaction happens between them, and if enough of them do it, the concentration of the reacting molecules will go down, while the concentration of the products goes up. In both cases, a lot of the collisions that occur have very little effect on the end result. One molecule hitting another doesn't mean a reaction's gonna take place, in the same way that just randomly bumping into another guy's car doesn't mean that you're gonna ram him out of the derby. So, what makes a collision effective? The hit has to be hard enough, and it has to be aligned just right. The branch of chemistry that studies how these collisions affect the rate of reactions is kinetics. And if you ask me, it's just as exciting and a heck of a lot more useful than demolition derby. If chemical reactions only work when particles bang into each other good and hard, just how hard do they have to bang into each other? Every reaction has a minimum amount of energy required to get it started. This is known as the activation energy. Molecules require this much energy to hit other molecules hard enough to break them apart and reform them in different ways. Without it, nothing will happen. It's like a hill that molecules have to get over before they can go any further. So where do they get this energy? Well, it's kinetic energy, the actual speed of the particles. So just like the cars at a demolition derby, all else being equal, the faster the particles move, the harder the collision will be. But still, no matter how hard they hit, it won't do any good if they're not hitting the right way, in the right places. Like if you keep smashing into the back of a guy's trunk, it's not gonna stop his car, there's no engine back there. You can bang Velcro together all day and night, and if it's not turned the right way, it'll never stick together. Same thing with molecules. As an example, take nitric oxide, one of the byproducts of gasoline combustion, and something that you can smell quite clearly at a demolition derby. Under the right conditions, it reacts with hydrogen gas to produce nitrogen gas and water. But the molecules have to hit each other just the right way. To make N2, two NOs have to collide in such a way that the nitrogens are together, and to get H2O, a molecule of H2 has to collide with the oxygen side of an NO molecule. Just like Velcro being turned the wrong way, you can smack the inside against the H2 all day and you'll never get any water from it. Now let's say that we're having a lot of solid, effective collisions between the molecules. The reaction should hum along with no further hindrances, right? Well, yes and no. Once the energy requirements are met, the reaction will proceed, but its speed, or reaction rate, will vary wildly from super fast to super slow.
Really what we're dealing with is how fast is a product being produced, or how quickly is something, a reactant, being used up. We're talking about the rate of change. So when we deal with concentrations, we're talking about the rate of change of the concentration, so we're dealing with moles per liter per second. How much does the concentration change per second? Now it's important to note that the rate is not constant, and if you think about this, it should make a little bit of sense. As we go through the reaction, the concentration or amount of reactants is going to decrease, while the amount of products or the concentration of products is going to increase. So when we deal with this rate, the rate of consumption of the reactants is actually going to go down because we have more and more of the reactant being used up and therefore less and less of it remaining. So the rate of this reaction is going to slow both in the use of the reactant and in the production of the product.
And this has to be determined experimentally. It can't be calculated from the energy change or any other thermodynamic factor. One useful way to think about the rate is a quantity called the reaction's rate law. It describes the relationship between the initial concentrations of the reactants and the rate at which they react. The rate law for a reaction is written like this. The rate equals a constant K times the concentrations of each reactant raised to some power. Notice that only the reactants are used for this, not the product.
If we look at the variables that we have in this rate law, we can see that the square brackets always denote moles per liter, and that we have the concentration of both of our reactants in there, A and B. Now, if there was a C and a D, those concentrations would also be considered in our rate law. So our rate law is as long as the number of reactants that we have in our particular reaction, because K is referred to as the rate law constant. And obviously that constant is going to be different for various reactions. The other thing that's important about K is that it's temperature dependent. that means that K is going to vary depending on the temperature of that overall reaction. If the temperature goes up, K will also go up. If the temperature goes down, K will also go down. So we don't want to change the temperature, that is, we want to hold it constant when we're trying to evaluate K through various experimental trials. And it's important to note that the order, and then ultimately the value for K, is dependent on experimental data. The units for K are dependent on the individual orders of the reactants, and ultimately the overall order of the reaction. So we can't derive the values for K until we've gone through and assessed and evaluated all of the experimental and empirical evidence.
A reaction is at equilibrium when its forward and reverse rates are equal, right? So if we were to find the reverse rate law for a reaction, it would take the same form as the forward one, but using the initial concentrations for the products rather than the reactants. Think of like an imaginary reaction A plus B yields C plus D. The lowercase letters represent the coefficients of the reactants and products. The forward rate law is K times the initial concentration of A raised to some power times the initial concentration of B raised to some power, and the reverse is the same, but with C and D in place of A and B. Notice that these exponents are not, however, the coefficients of the balanced equation. If it's that simple, why don't all reactions just go to an equilibrium state and stay there? Well, sometimes the reverse reaction isn't thermodynamically spontaneous for one reason or another. Sometimes the forward reaction is so vigorous that any reactants that might reform are immediately pushed back into products. Or the products might physically separate and have little chance of colliding at all, like when products separate into solids and gases. Often, though, it's just that the reverse reaction has such a high activation energy that the collisions are almost always ineffective.
Now, what about order? Well, in order for us to establish order, we have to, as I said, evaluate these things experimentally, and we have to use the empirical data. Now, the method that we use to do this is something called the initial rates method. And really what we're doing is just taking different concentrations of the reactants and measuring a short amount of time between the initial concentration and some endpoint. So we change the concentration and see how quickly or slowly the rate goes after changing that.
Suppose we did the reaction a few different ways and calculated the rate for each instance. Let's say that with the first reaction we got a rate of 0.0060 moles per liter per second. Then we repeat the reaction with the same amount of nitric oxide, but this time with twice as much hydrogen as before. And now we find that the rate of the reaction is 0.012 moles per liter per second. What does this tell us? Well, doubling the hydrogen doubled the rate, meaning that the rate and the H2 concentration change in exactly the same way. So in the rate law, this can be expressed by the concentration being raised to the power of 1. Finally, we do it one last time with the original amount of hydrogen, but twice as much NO. And this time we find that we get a rate of 0.048 moles per liter per second. Doubling the nitric oxide caused the rate to increase by 8 times, and that can be expressed in mathematical terms by cubing the concentration term. This means that the final rate law for this reaction is K times the concentration of hydrogen gas to the first power, you don't need to write out the 1 obviously, times the concentration of nitric oxide cubed. A rate law in this form is said to be of the 4th order. We get that value by adding the exponents together, 3 plus 1. There is some math that isn't hard here. That equals 4. 4th order reactions are actually quite rare. Most reactions are of the 0, 1st, or 2nd order, but in all cases it's calculated exactly as we have done here.
Now, these orders that are derived from our experimental data, what they do is they give us a relationship between the concentration of the reactants and the overall rate of the reaction. If we have something that we refer to as 0 order, 0 order means that the concentration or a change in concentration is going to have effectively no change in the rate of the reaction. So even if we were to double or triple or quadruple the overall concentration of that particular reactant, if it's 0 order, it's not going to have any effect on rate. If we have something, however, that's 1st order, that's a direct relationship between the concentration and the rate. So if something is doubled in terms of its concentration, we will notice a doubling in the rate as well. And when we get into something that is 2nd order, we now raise any change in concentration to the power of 2, or we square it, so that if we were to double the concentration, we would get a quadrupling in the overall rate.
Most reactions don't happen instantly, boom, all at once. Instead, they happen in steps. And as with any multi-step process, the reaction can only happen as fast as the slowest step takes. And sometimes that step is very slow indeed. Since it's what controls how fast everything else can go, we call it the rate limiting or rate determining step. The slowest step is the one that has the highest activation energy. If the particles have trouble getting over that part of the energy hill, then they'll have trouble making it to the finish line no matter how fast the other steps are. So in the case of the nitric oxide reaction we've been discussing, there are actually 3 steps. First, the nitric oxide and the H2 form water and elemental nitrogen. Then, the nitrogen combines with another molecule of NO to form N2 and elemental oxygen. Finally, that atom of oxygen combines with another molecule of H2 to form water. Here, step 2 is the slow one, and no matter how fast you take the first step, the water product can never be produced until the nitrogen gas is. Problem is, we can't always afford to wait around for reactions to happen on their own. Sometimes they need to be forced along, and that's the job of catalysts. A catalyst is a chemical that lowers the activation energy of a reaction, thereby speeding it up without actually being changed by it. Catalysts take many different forms. They can be just another chemical added to the reaction vessel, a piece of metal that's in contact with the reacting chemicals, or even a gas that's added to the environment. One of the most common and important classes of catalysts are the enzymes in living things. Without them, many of the chemical processes that our bodies must do every day to keep us alive would slow essentially to a stop. We literally could not survive without them. So there you go. In demolition derbies and in chemistry, it all comes down to how hard you can hit and how well you can aim your punches. Chemistry. Surprisingly exciting, even without funnel cake.